In just 143 days, Lockheed achieved what many thought impossible, designing and building the P-80 Shooting Star, America's first operational jet fighter. This remarkable aircraft broke new ground in aviation history, reaching speeds of 502 miles per hour at 20,480 feet, making it the first turbojet-powered United States Army Air Force's aircraft to exceed 500 miles per hour in level. The Lockheed P-80 Shooting Star notably demonstrated its combat prowess during the Korean War, where it was responsible for 75% of enemy losses in the initial months of the conflict. Furthermore, this revolutionary P-80 fighter introduced several engineering breakthroughs, including the first ejection seat in a production U.S. aircraft. With a service ceiling of 45,000 feet and powered by a General Electric 140 turbojet engine producing 3,800 pounds of thrust, the P-80 aircraft set new standards in military aviation technology. Join us as we uncover the engineering marvel that redefined military aviation and set the stage for the jet age. The race to build America's first jet fighter. In the spring of 1943, Allied intelligence uncovered Germany's development of the Messerschmitt Me 262, marking a critical turning point in aviation warfare. This discovery prompted immediate action from the U.S. Army Air Force, as the Me 262's superior capabilities posed a significant threat to Allied air superiority. The Me 262 emerged as the world's first operational jet-powered fighter aircraft, demonstrating unprecedented capabilities in combat scenarios. Initially, German pilots claimed 542 Allied aircraft shot down using the Me 262. The aircraft's superior speed and heavy armament, which included four 30mm nose-mounted cannons, made it a formidable opponent against Allied fighters. Subsequently, General Henry Arnold recognized the urgent need for a countermeasure to the German jet threat. After receiving British jet aircraft research documents, Arnold approached Lockheed to design an airframe compatible with the British-made Halford H-1B Goblin jet engine. In response, Clarence Kelly Johnson submitted a bold design proposal in mid-June 1943, committing to deliver a prototype in 150 days. Consequently, Johnson established a unique development environment for the P-80 Shooting Star project. The team operated from a rented circus tent positioned downwind from a plastics factory in Burbank, California. This location, primarily chosen to deter curious onlookers, became the birthplace of the legendary Skunk Works division. The project maintained exceptional secrecy levels, with only 5 team members among the 130 personnel aware they were developing a jet aircraft. Additionally, the British engineer delivering the Halford H-1 engine faced temporary detention because Lockheed officials could not verify his identity. Under Johnson's leadership, the 28 engineer team worked following the same autonomous principles that had proven successful with the P-38 Lightning II. The development process demanded intense dedication, with team members working 10 hours daily, 6 days per week. This commitment paid off when the team completed the P-80 aircraft in 143 days, surpassing the original deadline. The project's success established new standards for aircraft development, primarily through its innovative approach to design and manufacturing processes. Revolutionary design features of the P-80. The Lockheed P-80 Shooting Star stood out with its revolutionary design features that set new standards in military aviation. The aircraft's innovative engineering solutions marked a significant departure from conventional fighter designs of its era. The P-80 aircraft featured a conventional all-metal airframe with a distinctive slim low wing and tricycle landing gear configuration. The fuselage incorporated flush rivets and smooth skin, creating an aerodynamic profile that minimized drag. Rather than following traditional construction methods, the P-80 Shooting Star's airframe utilized aluminum alloys, achieving a maximum takeoff weight of 16,000 pounds. One unmistakable innovation came through Kelly Johnson's patented wingtip fuel tanks. The P-80 fighter became the first aircraft in the world to incorporate tip tanks, which served multiple purposes. These shapely, tapered tanks reduced total drag by acting as wingtip end plates and diminishing tip vortices. Moreover, they enhanced roll response and improved the span-wise loading of the wing. The engineering team solved a critical intake duct challenge by developing an innovative solution. After identifying turbulent boundary layer interference with smooth airflow into the engine, they created a distinctive louver-like, boundary layer reading air scoop positioned inside the intakes. This modification primarily addressed the powerful low-pressure area inside each duct that had initially caused structural concerns. The P-80 Shooting Star marked a historic milestone as the first operational jet fighter to feature its engine buried within the fuselage, a design approach pioneered by the German Heinkel He-178V1 in 1939. This innovative configuration proved so effective that it became the standard for nearly all subsequent fighter aircraft. Over its development, the P-80's propulsion system evolved significantly. The initial prototype was powered by the British Halford H-1B Goblin engine, later replaced in production models by the General Electric I-40 turbojet, which delivered 3,800 pounds of thrust. The final variant featured the more powerful Allison J-33A-35 engine, producing 4,600 pounds of thrust. This powerful propulsion system enabled the Lockheed P-80 Shooting Star to achieve remarkable performance metrics. The aircraft reached speeds of Mach 0.76 and maintained an operational range of 825 miles. As opposed to contemporary fighters, the P-80 jet's engine placement and integration created a more streamlined profile, contributing to its exceptional speed capabilities. Engineering challenges and solutions. Development challenges plagued the early stages of the P-80 Shooting Star project, demanding innovative solutions from Lockheed's engineering team. The aircraft's journey from concept to reality encountered numerous technical hurdles that required quick, effective responses. The integration of the British-made Halford H-1B engine presented significant challenges. Despite careful planning, the initial engine installation resulted in catastrophic failure. The British engineer who delivered the engine had warned about the intake duct structural weakness, although Lockheed's team initially dismissed these concerns. Primarily, the problem stemmed from insufficient duct thickness, which led to a collapse during the first full-throttle test. The engineering team discovered that turbulent boundary layer interference disrupted smooth airflow into the engine. Therefore, they developed a specialized boundary layer reading air scoop system, which became a standard feature in all subsequent production models. Structural challenges with the P-80 Shooting Star extended far beyond the complexities of integrating its revolutionary engine design. The aircraft required significant modifications to ensure it met stringent operational safety standards, addressing both immediate issues and long-term reliability. One critical focus for the engineering team was restoring the original static strength and stiffness in areas affected by wear or damage during service. Simultaneously, efforts were made to implement fatigue resistance improvements, a crucial factor given the high-performance demands placed on jet fighters. Enhancing damage tolerance capabilities was another priority, ensuring that the aircraft could sustain and recover from minor structural compromises without jeopardizing its flight performance. To further bolster safety and reliability, engineers developed more rigorous inspection protocols to identify and address potential issues before they escalated. Central to these efforts was the SkinFix program, an advanced two-dimensional compatible displacement analysis tool. This cutting-edge system allowed the team to calculate skin and doubler stresses with remarkable precision. In regions subjected to modest load transfer, SkinFix achieved an impressive 95% accuracy, enabling precise and efficient repairs. However, in areas experiencing higher load transfers or significant out-of-plane bending, the tool's accuracy dropped to 85%, revealing the ongoing challenges of analyzing complex stress patterns in high-performance aircraft. Despite these limitations, SkinFix represented a major leap forward in aerospace engineering, playing a vital role in extending the service life of the P-80 and solidifying its reputation as a technological milestone. Material selection played a crucial role in addressing the P-80 fighter's structural challenges. The engineering team developed a comprehensive methodology for analyzing repairs and material choices. Nevertheless, this process required extensive testing, including strain gauge Type 3 repair panels and precise measurements of rivet displacements under load. The development team behind the P-80 Shooting Star introduced groundbreaking quality control protocols for material selection and implementation, setting new standards in aerospace engineering. These protocols prioritized a realistic analysis of stress history at specific fuselage locations, ensuring the aircraft's structural integrity under operational conditions. Limit load analysis techniques were also employed, enabling engineers to assess and verify the airframe's ability to withstand maximum expected stresses during flight. Additionally, the team developed advanced probabilistic modeling methods to evaluate the performance and reliability of aged aircraft components, accounting for wear and tear over time. The Lockheed P-80 Shooting Star's engineering evolution demonstrated the importance of systematic problem-solving in aircraft development. The solutions developed for these challenges influenced future jet aircraft design and manufacturing processes, establishing new standards for military aviation engineering. The P-80's groundbreaking propulsion system. The propulsion system of the P-80 Shooting Star marked a pivotal advancement in American aviation, primarily through its innovative adaptation of British jet engine technology. General Henry H. Arnold's discovery of the Whittle-powered Gloster E-2839 prototype in April 1941 set the stage for this technological leap. The P-80 aircraft's power plant evolution began with the British-designed de Havilland Goblin engine. Accordingly, the British provided two Goblin engines, originally intended for the de Havilland Vampire. The engine development process faced significant hurdles, as the first engine was destroyed after foreign object damage during initial testing. General Electric, leveraging its extensive expertise in turbine technology, played a pivotal role in the development of the J-33 turbojet engine, which would power the P-80 Shooting Star. The engine specifications underwent significant evolution during the aircraft's development. The initial XP-80 prototype was equipped with the de Havilland Goblin engine, marking the beginning of its jet-powered journey. For production models, this was replaced by the General Electric I-40 turbojet, which delivered 3,800 pounds of thrust and brought the P-80 to operational readiness. In advanced variants, the aircraft featured the Allison J-33A-35 engine, a more powerful system producing 4,600 pounds of thrust, which further enhanced its performance and cemented its legacy as a cutting-edge fighter of its era. The P-80 fighter incorporated groundbreaking cooling solutions to manage the intense heat generated by its jet engine. Simultaneously, the engineering team developed an innovative boundary layer control system to ensure proper airflow and cooling. This system proved crucial in maintaining optimal engine performance and preventing the structural failures that had plagued early prototypes. The cooling system design addressed multiple challenges, particularly in managing the powerful low-pressure areas within the intake ducts. At the same time, the engineers implemented specialized air scoops just inside the intakes, effectively managing the turbulent boundary layer that had initially disrupted smooth airflow into the engine. The Lockheed P-80 Shooting Star's fuel system represented a significant leap forward in aircraft design. In particular, Kelly Johnson's patented tip tank innovation became a defining feature of the aircraft. These tanks served multiple purposes beyond fuel storage. They reduced total drag by acting as wingtip plates and improved the aircraft's roll response. The original tip tank design featured a 165-gallon capacity with a rounded nose and sculptured afterbody. The final iteration of the F-80 tank increased capacity to 230 gallons and incorporated a side-mounted fin on the afterbody. This enhanced fuel system extended the P-80 jet's operational range while simultaneously improving its aerodynamic performance. The fuel system underwent continuous refinement, with later models featuring a more economical design from Fletcher Aviation. These modifications maintained the essential performance benefits while reducing manufacturing costs and simplifying maintenance procedures. Manufacturing innovations. Under the leadership of Kelly Johnson, Lockheed's manufacturing process for the P-80 Shooting Star established new benchmarks in aircraft production efficiency. The project's unique development environment, housed in a rented circus tent in Burbank, California, set the stage for groundbreaking manufacturing innovations. The first thing to remember, the P-80 aircraft's production process introduced unprecedented assembly line techniques. The engineering team worked 10 hours daily, 6 days a week, under strict secrecy protocols. As a result, they completed the XP-80 prototype in 143 days, 7 days ahead of the original schedule. The manufacturing process primarily focused on rapid prototype development and efficient production scaling. The Lockheed team's excellent performance figures and short production period warranted an immediate go-ahead on the project, with a letter of contract issued within 6 days. Given these points, the engineering phase began in May, followed by thorough inspections at Lockheed's Burbank plant in July. The P-80 fighter's manufacturing process essentially revolutionized quality control standards in aircraft production. The team implemented rigorous inspection protocols throughout the assembly process. Overall, these quality control measures proved highly effective, as demonstrated by the successful completion of the first prototype in 132 days. The manufacturing team devised specialized testing procedures to ensure the P-80 Shooting Star met the rigorous demands of operational performance and safety. These procedures included comprehensive structural integrity verification to confirm the aircraft could withstand the stresses of high-speed flight and combat conditions. Engine integration validation was also a key focus, ensuring seamless compatibility between the airframe and the turbojet engine. Flight characteristics assessments were conducted to evaluate the aircraft's overall aerodynamic performance, while stability and control testing ensured the P-80 remained reliable and responsive during various maneuvers. The Lockheed P-80 Shooting Star's production numbers reflected its manufacturing success. The initial production order comprised 344 P-80 as after United States Army Air Force's acceptance in February 1945. By the end of production in 1950, Lockheed had manufactured 1,714 single-seat F-80A, F-80B, F-80C, and RF-80s, including 920. The production schedule for the YP-80s demonstrated remarkable efficiency. The Army Air Forces initially requested 13 airframes to be delivered by March 1945, yet Lockheed expedited the delivery schedule, completing the order by December 1944. The two-seat TF-80C variant, introduced in March 1948, became the foundation for the T-33 trainer, with 6,557 units. The P-80 jet's manufacturing success extended beyond American borders. Lockheed's total production reached 5,819 aircraft, with additional units built under license in Canada and Japan. This made the P-80 Shooting Star the most produced Western turbojet aircraft of its time, second only to the F-86 Sabre/FJ Fury series. Flight testing and refinement. Flight testing of the P-80 Shooting Star revealed both the aircraft's potential and its early vulnerabilities. The testing phase, beginning in January 1944, marked a critical period in American aviation history, with Lockheed test pilot Milo Burcham conducting the maiden flight. The initial testing phase encountered significant setbacks. Primarily, the first flight lasted merely 5 minutes due to landing gear retraction issues. After all, this proved to be a minor concern compared to the tragic events that followed. The P-80 aircraft's development cost several lives, beginning with Chief Test Pilot Milo Burcham's fatal crash in October 1944 due to fuel pump failure. Indeed, the testing program faced mounting challenges when Tony LaVere, Burcham's successor, narrowly escaped death after his P-80 fighter's engine disintegrated, causing structural failure in the tail section. Before long, these incidents prompted intense scrutiny of the aircraft's safety systems and operational protocols. The Lockheed P-80 Shooting Star demonstrated remarkable capabilities during its performance testing. Soon, the aircraft achieved a speed of 502 miles per hour at 20,480 feet, establishing itself as the first United States Army Air Force's turbojet-powered aircraft to exceed 500 miles per hour in level flight. A specially modified P-80R Racer variant eventually set a world airspeed record of 6. The testing program for the P-80 Shooting Star expanded to encompass a range of ambitious trials, including coast-to-coast flights across the United States from Long Beach to New York in 1946. These efforts demonstrated the aircraft's endurance and reliability over long distances. The program also included transatlantic flight demonstrations, showcasing its advanced capabilities on the international stage. Additionally, modified naval variants underwent carrier landing trials, exploring the feasibility of adapting the P-80 for naval operations and highlighting its versatility as a cutting-edge jet fighter. After America's top ace Richard Bong's fatal crash, General Arnold ordered comprehensive safety modifications. Certainly, this led to rigorous testing protocols, with 5 handpicked P-80 as undergoing extensive 50-hour flight evaluations. The improvements addressed several critical areas. The P-80 jet underwent significant safety enhancements, undoubtedly focusing on fuel system reliability. The engineering team implemented an auxiliary I-16 fuel pump system, though pilots needed manual engagement during operation. Generally, these modifications proved successful, as demonstrated when test pilots Robert E. Thacker and Chuck Yeager completed 500 hours of incident-free testing on 5 different aircraft. Jack Sullivan's harrowing test flight in 1946 highlighted the importance of emergency procedures. Finally, his experience led to improved pilot training protocols and enhanced emergency response systems. The P-80 Shooting Star's testing phase ultimately established new standards for aircraft safety evaluation and pilot training procedures. Combat Performance Analysis. The P-80 Shooting Star marked its combat debut in the Korean War, where it significantly shaped early air operations. The United States Air Force deployed 10 squadrons equipped with F-80 Sea-to-Kes, primarily operating from bases in Japan and South Korea. The P-80 aircraft dominated early air operations, accounting for 75% of enemy losses during the initial months of the Korean campaign. The 8th Fighter Bomber Wing, based at Suwon Air Base, emerged as the longest-serving F-80 unit in Korea, conducting missions from June 1950 until May 1953. The Lockheed P-80 Shooting Star's operational tempo peaked when the 36th Fighter Bomber Squadron set a record for daily combat sorties, executing 121 missions in a single day. The P-80 fighter secured several historic achievements in aerial combat. On November 8, 1950, Lieutenant Russell Brown achieved the first American jet-versus-jet aerial victory, claiming a MiG-15. However, 1 week earlier, Soviet pilot Lieutenant Semyon F. Kamenich had already made history by becoming the first pilot to score a jet-versus-jet kill, reportedly downing an F-80. The P-80 Shooting Star's combat record is marked by notable achievements, including 17 aerial victories in which enemy aircraft were destroyed in air-to-air combat. Additionally, the P-80 played a crucial role in ground attacks, eliminating 24 enemy aircraft while stationed on the ground. In encounters with the advanced Soviet MiG-15 jets, the P-80 achieved 6 confirmed victories, demonstrating its effectiveness even against more modern adversaries. Markedly, the P-80 jet excelled in ground attack missions after being reassigned from air superiority duties. The aircraft carried an impressive array of offensive weapons, including 6 nose-mounted 0.50-inch machine guns, unguided rockets, conventional bombs, napalm. The P-80 Shooting Star's ground attack capabilities proved crucial in disrupting enemy logistics and providing close air support. The aircraft's effectiveness came at a cost of the 277 F-80s lost in combat operations. 113 fell to ground fire, while 14 were downed by enemy aircraft. By the conclusion of hostilities, the Lockheed P-80 Shooting Star's combat record reflected both its capabilities and limitations. The total losses amounted to 368 aircraft, comprising 277 combat losses and 91 non-combat casualties. Hence, this represented approximately 30% of the existing inventory. Nonetheless, the aircraft's contribution to the war effort earned significant recognition, exemplified by Major Charles J. Loring Jr.'s posthumous Medal of Honor for his actions while flying an F-80 with the 80th Fighter Bomber Squadron. Legacy and impact. Beyond its immediate military impact, the P-80 Shooting Star established enduring benchmarks in aviation technology and manufacturing processes. The aircraft's influence extended far beyond its operational lifespan, shaping the future of jet aviation across multiple domains. The P-80 aircraft's design philosophy primarily influenced subsequent jet fighters, establishing fundamental principles for future aircraft development. The success of Kelly Johnson's patented wingtip fuel tanks led to widespread adoption of this technology across various aircraft designs. In essence, the P-80 fighter's achievements demonstrated America's commitment to advancing aviation technology and ensuring air superiority. The Lockheed P-80 Shooting Star's impact on future designs manifested through several key innovations. The aircraft's streamlined fuselage construction and advanced aerodynamic solutions became standard features in subsequent jet fighters. Likewise, its engine placement and integration methods established a template that influenced generations of military aircraft. The most enduring legacy of the P-80 Shooting Star emerged through its trainer variant, the T-33. This adaptation involved extending the P-80 airframe by 4 feet 6 inches to accommodate an instructor pilot, transforming the aircraft into a versatile training platform. The T-33's remarkable production numbers underscore its success, with a total of 6,557 units manufactured and widespread adoption by. Further demonstrating its global impact, an additional 650 units were produced under license in Canada. Remaining in production until 1959, the T-33 became a cornerstone of pilot training programs worldwide. The T-33's influence on military aviation training proved substantial, as it trained an estimated 250,000 new jet pilots. Similarly, the United States Navy procured 698 T-33 Shooting Stars for carrier-based training operations. In contrast to modern practices, where advanced flight simulators have eliminated the need for two-seat trainers, the T-33's hands-on training approach set industry standards for decades. The manufacturing processes developed for the P-80 jet established new paradigms in aircraft production. The Skunk Works division, under Kelly Johnson's leadership, introduced revolutionary approaches to aircraft development and production. Their 14 rules and practices continue to influence modern aerospace manufacturing. The success of these manufacturing innovations became evident through several achievements. The P-80 Shooting Star's production demonstrated unprecedented efficiency, with Lockheed manufacturing 1,714 single-seat variants. Ultimately, this manufacturing success extended globally, with total production reaching 5,819 aircraft, making it the second most produced Western turbojet aircraft of its era, surpassed only by the F-86 Sabre or FJ Fury series. The manufacturing legacy of the Lockheed P-80 Shooting Star continues to influence modern aircraft production. For instance, the Skunk Works approach to streamlined development and production processes has shaped programs like the F-35, which emphasizes automated production facilities and efficient manufacturing techniques. The division's reputation for solving complex problems quickly and affordably remains a benchmark in aerospace manufacturing. The P-80 fighter's development also established new standards for project management in aerospace manufacturing. The Skunk Works model, characterized by small, empowered teams and streamlined processes, has been adopted by numerous aerospace companies. This approach has proven particularly valuable in developing advanced aircraft systems that push technological boundaries while maintaining cost-effectiveness. The aircraft's influence extends into modern times through the Skunk Works division's continued innovation. Their achievements include 8 Collier trophies, awarded for the greatest achievements in aeronautics or astronautics in America. Furthermore, Lockheed Martin received prestigious recognition in 2007 for their exceptional record in developing cutting-edge aircraft and technological solutions. The Lockheed P-80 Shooting Star is a true symbol of American engineering and innovation, revolutionizing aircraft manufacturing under Kelly Johnson's leadership and the Skunk Works division. Its pioneering features, such as the ejection seat and wingtip fuel tanks, set new standards in military aviation. In the Korean War, the P-80 played a key role in securing 75% of enemy losses early on. Its transformation into the T-33 trainer further shaped pilot training globally, preparing over 250,000 pilots. The P-80's legacy goes beyond its success, influencing modern aerospace development and proving the power of small, agile teams. What do you think was the most groundbreaking feature of the P-80? Let us know in the comments. Thank you for watching.